How's the programming challenge? Good. You cooked. Okay. Oh, cool. Cool. Okay. So, I guess that brings us right to course logistics. So, obviously, challenge 1 is due today. So, you should try to do that today. If you don't do it, remember each day, like starting with Monday, it's 10 points off of the total that you can get. So if you're not doing it today, definitely try to do it Monday to kind of maximize that or minimize the point loss maximum time. So today we will talk about trees, more about trees, and a little bit of a spoiler alert. All of next week we will talk about trees. So different types of trees, but the basic tree structure. So today we will look at some more of the general parts of trees that will apply to everything that we do. And then next week we will get into specific types of trees, and we'll start with binary search trees, which are pretty useful. So last time we discussed some of the basics of trees. And in terms of the data structure itself, the important things to remember are that the trees are made up of these nodes, just like our linked list are made up of nodes. Each node storing some data, and each node having links to children nodes. So it's kind of a hierarchy of a structure. And so these links will be implemented, and we're in C++, as a pointer, similar to how linked lists we implement the linking with a pointer. So we'll talk about more trees today. We'll start by going through the tree terminology, which there is a lot of. It's pretty intuitive, I think, and it's good to know just to be able to quickly understand a question or something about one of these particular nodes. So just to kind of briefly go over some of the things we talked about last time. So we had the idea of a parent node being like N1 being the parent of N2 and N3. We had the idea, obviously, of a child, so N2 and N3 being children of N1. And then we had the broader concepts of ancestors and descendants. So an ancestor of NB would be, anything in the chain all the way up to N1. And a descendant of N1 would be anything under N1. And you could pick any node in here and do that. So for a tree, we have a special node that we consider the root node that only has descendants. It does not have a parent. And as we implement that in code in C++, that typically looks like the parent reference being null for that particular node. And so when we draw a tree, we typically draw the root at the top and then branch out as we go down the page. So let's see. Leaves, another term that we use a lot with trees, are any of the nodes that don't have any children. And so you can kind of see the metaphor there, leaves of a tree. And that would be these nodes that are shaded in green all along the edges here. Branches, which typically can be called internal nodes as well. And they are things that are in between the leaves and kind of the root, but they have both ancestors and descendants. And so you will see them called both things, either an internal node or a branch. Okay, so a degree of a node is the number of children that it has. So here I've just labeled this tree for each node. This is the number of children that the node has, and so that's the degree of the node. And in this case, it's the number of edges coming out of these nodes, right? And that's just how many children that it has. And the depth of a node. And so this is the number of edges between the node and the root. And these are all labeled with their depth, and you can kind of see a trend here, which leads, I think, into the next concept, is the idea of a level. So nodes at the same depth, we consider those a level, so a little bit simpler than having to kind of label everything like this. When we have a tree that's sizable, you'll see it labeled kind of over to the side just at these different heights. And you can segment this with lines if it gets complicated, but everything that's at the same depth is considered at the same level, and we start at 0 with the root being at the 0 level. Okay, so somewhat related is the height of a node, and it's the length of the longest path from it to any node. So what you're looking for, like in the case of the root here, it will be the height of the tree, because anytime we talk about the root, that kind of applies thing to the whole tree, right? So you're looking for the longest path to any node, and if you follow this down, you will find we can exhaustively check all of these, right, as we look at it, and see what that is. And in this case, it's 3. Yeah. And so that brings us to kind of one of the most important concepts as we start to talk about trees and look at them in more depth and implement them. And that's the idea of a subtree. And the idea of trees being very recursive in nature. So just kind of a quick survey. In your prior classes, have you done recursion much, programming a little bit? Okay, yes. Yeah. So it's very similar, and you'll see when we write code for trees that recursion is a very natural way to deal with a tree. But the idea that we can think about it like graphically or just looking at this, right? So this whole thing is a tree, but obviously, like, let's just segment off like this section, right? Well, this could be a tree too, if we're just looking at it. And so you can think of these as sub-trees within a tree. And that turns out to be a powerful way to use this data structure, and kind of is what ultimately buys us a lot of efficiency gains, is the fact that we can divide problems up recursively like this. And in particular, what turns out to be, I would say, the most helpful is just being able to do a binary division. So a binary tree where we just have 2 children at most for each node. Okay, so let's talk a little bit about finding the depth of a node and how we would do that in code. So this is just pseudocode. This is not a particular language or anything. But if we remember that the depth is the number of edges between the node and the root, we can think about how we would write code to do that. And there are certainly a number of approaches we could take. But let's just assume, and this will be the case for the things we implement, and is the case for most things in like a standard library, is that for every node, we have a pointer to its parent node, if it has a parent. So the only node that doesn't have a parent is the root. Yeah, the root. So, and in that case, like in a practical sense, probably will be null. But what we can do is, rather than do this in an iterative fashion, we can write a function that kind of leverages that recursive nature of things, right? And so each node itself will know if it is a root, it is the root node, or if it has a parent. And so we can kind of take a recursive approach where our base case in this function, if you remember when you learn recursive stuff, the most important part is the base case, right? So that you terminate the function eventually. And so our base condition is if our node is the root node, we're going to return 0. Otherwise, we're going to return 1 plus the depth of our parent node. And so you can kind of trace this out pretty easily in like a small tree like this. So the idea here is that you would receive a reference to a node. And so let's just say that that node is n5 in this case. And so when we come through here, we have n5. It's not the root. So we go here, we return 1 plus the depth of n4. Same thing there, n4 comes through here. It's not the root. 1 plus n2, then when n2 comes through, 1 plus n1. And then n1 is finally the root, so that returns 0. And so then that whole chain adds up, right? And we get our depth of 1, 2, 3. So that's just kind of a naive recursive approach here to finding the depth of a node. As to why you would want to find the depth of a node, we will talk about that more next week. But know that kind of the idea of subtrees within trees and the recursive nature is very useful and important as we start to work with these structures. So thinking about the computational complexity of this, this is a little bit of a weird one, at least for me to think about, I think. So the big O, big theta is order of n, and n being the number of nodes in the tree. Now, on average, that's probably not going to be the runtime. So you've got to think about this in terms of kind of the worst case here is you have a tree where like you don't have n3 and maybe you don't have n6, right? It's just like a straight line, like it's like a linked list really, right? And in that case, your depth is going to need to go through all of those nodes. Now, in reality, this is more, I mean, it's, you know, if we could have the answer ahead of time, you know, it's the number of levels that are there, right? But the whole point is that we don't, and so in the worst case, it would be all of these nodes that are in the tree. But this is one where it's easy to see how the worst case is definitely probably not the most common case that occurs, because usually when we use a tree for something, we don't just put things in there randomly. We have some heuristic or some way that we're sorting that tree out. And that lends itself to properties that do not result in a linear linked list as our tree kind of structure. So these are things to think about that we will see with more like detail as we implement this. We'll kind of come to appreciate the nature of like the theoretical worst case and then the worst case that we kind of see a lot in practice. Questions so far about trees? Good? Yeah?
Go through the pseudocode again?
Yeah. So what we're doing is we're going to take as an input to this function any node in the tree. And then what we're going to do is first check if it's the root, right? So if we fed in the root node, right, like n1, well, its depth is 0, right, because it's at the top, so we just return 0. We're good. But if we, let's say it was just n3, right? So we come in with n3, it's not the root. So instead of returning 0, we return 1 plus the depth of its parent. So now we have to look at n3 and say, like, okay, what's your parent? Its parent is n1. So now we have 1 plus the depth of n1. So depth of n1 comes through, n1 is the root, 0. So it's then 1 plus 0 returns. Does that make sense? Yes. Yeah. So, I mean, this is, recursion is really interesting. If you ever get a chance to like use a purely functional programming language, when I was an undergrad, the professor who really liked a language called Haskell. I don't know if any of you, yeah, Haskell fan? Yeah, it's fun. It's a real challenge to think about things in that way. And so, yeah, recursion is a big part of it. And it's very mathematical in a sense. Like you can almost kind of see the programs as equations rather than code. So, yeah, it's definitely an interesting way to think, and then analyzing it for the complexity can be a lot more interesting than this. But we'll do some of those. Also, you may realize that as we're entering this territory, and we're kind of looking at these trees, mostly thinking about just the binary case, like where we have 2 children, you start to see where we talked about in complexity, like having log n as the complexity, and that is where that usually comes from, is this dividing things by 2 leads us down that path, and we'll see that in detail later. Okay, so the main thing that I want us to do today is to conquer this idea of tree traversals. And it's a pretty basic thing, and it's like one of the first things you need to do when you implement this, right, is you need to be able to see it somehow. And it's similar to how we would do like a linked list, where we start at the beginning, or maybe we start at the end, and we follow the links, and as we move to a node, we print out the value in that node, then we move to the next. So with trees, we have more choices, as you can see, in terms of how we do this, right? So assuming we just start at the root, like we always have a pointer to the root, right? Well, immediately, in this example, we have 2 choices, right, as to where we go next. And so you can imagine if we have more than 2 children, we have even more choices. But there are 3 common ways of traversing the tree. And traversing just meaning visiting every node, visiting, printing it, accessing it, going through the entire data structure. So the 3 common ways of doing this that you'll see kind of in like every book and every course about this, we have the pre-order, the in-order, and the post-order. And so let's just go through them and talk about the approach that each takes. So we'll use this example tree. So I'm going to start with the pre-order. And the idea here is that first you visit the node, and then you visit the descendants. So if we're starting at the root, first, obviously, we would visit the root. Visiting meaning, in our case, we're printing it. It could just be that you're accessing it, anything like that. But we start at the root, and so the first thing we do is we print it. Now, next, we've got kind of this vague idea of visit the descendants, right? Well, here's the choice. And so, kind of as a matter of convention here, we're going to say, like, as we are viewing this, we're going to go to the left, our left, as we're looking at this structure. If we were the tree, it would be on the right, so stage right, I don't know. Tree right, our left. And so I'll tell you that these traversals, I'm going to do this with a couple of these nodes that have like 3 children. For the most part, you're only ever going to do this with binary trees, and we'll see why. But you can do it with as many as you want. Okay, so we visited the first one, and now we're going to go to the descendants. So now we arrive at N2, which is a descendant, and so we print out N2, we visit N2, and then we have kind of the same instruction here, right? Visit the descendants of N2. So we go ahead and we follow that heuristic of we're going left, our left, and we go to N4. Can you guess where we go next?
N9.
Yes, N9. Okay, so now we've gotten to a node finally that doesn't have any descendants. What do?
We go back up and see if we can go right.
Let's see. Yes, right. So yeah, we came down here, we visited M9, and then there was nothing else to do, so we come back up, and N4 still says I need to visit my descendants. It's got 2. We visited M9, so we come down here to NA. Now, once we're done with NA, we're going to do a similar thing, right? We're going to come back up here, and we're going to say, okay, does N4 need to visit any descendants? No, we visited all of them, right? So now that's going to bounce us back up here to N2. Does N2 need to visit descendants? Yes. And so we'll visit, in this case, N5. Then we'll come back up to N2, Got one left there, N6. Okay, so now we've kind of conquered this left side of the root structure. So we will propagate back up, right? And now we're asking N1, are there other descendants to visit? Yeah, we've got this whole subtree over here. So we'll come down to this subtree. And so remember, first we visit the node. So as we come through N3, we're going to visit it, and then we're going to its descendants. So in this case, we go to N7 because we're going to the left first, and then N7 only has the one descendant. We go there, and then finally, we'll come back up here. There's no other descendants. We'll come back up here, and there's one descendant there. And we're done. And so this is considered the pre-order traversal. Questions about that? Okay. All right, so now we have the in-order traversal. And you'll notice that my tree has conveniently changed to be a binary tree at this point. Not because you can do an in-order traversal of a tree that has more than two children in a node, but it's a little bit more of a choice as to the order in which you do things. And it's typically not something that we do or need to do. So the idea of the in-order traversal is that we visit the left descendants first, and then we visit the nodes. So it's kind of just flipping that order. So let's start with our root, or sorry, not with our root. We're starting with our root, but we kind of gave it away. So the idea is, okay, we're at the root. The first thing we need to do is visit any of the left descendants that it has, right? And so that first left descendant is N2. Okay, so we're at N2. Now we have the same instruction. Visit any of the left descendants that it has. Well, it does have N4, right? And so this is, again, is kind of that subtree thing, right? You can think of these each as being like applied to its own tree, if you'd like. But we're just kind of going down here until we get to N9, which does not have any descendants on the left. And so that condition is met, and then we move on, and it says visit the node. So we visit N9. Okay, so now, what do we visit next?
N4, and then we'll output it.
Yes, good. Right, so we were at N9. We did what we needed to do here. We're all done. So we come back up here, and the instruction is to visit this node before we visit the right node. So the order is left, the node itself, and then right.
So is this the same as we just did on slide 40?
So it's slightly different. So in the one before this, we visited the node first. So we always printed it first, and then we went to the left. So this time we'll do any children to the left, and then after that we'll do the node itself, and then after that any children to the right.
And that's a binary tree. So what was the tree before this?
So the tree before this, the tree itself, I'm not really sure what you would call it. It's not uniform in its amount of children that each node has. Like the node that had 3 would be a tertiary tree, but it's kind of just a tree that is a tree. It doesn't have a strict label that I'm aware of. I'm sure there is a strict label.
But like binary trees always work like this.
Yes, yeah. Binary tree, you'll always have a left and a right, or 1 and 2 children for each node. Okay, so we are going through this. 1, 2, we printed N4, and so the next thing is to visit the right descendant, which we do have. And so we'll visit that. Now, NA doesn't have any left, doesn't have any right. So we're going to come back up here, here everything's been done, so that will bring us back up here, where we have already done the first part, which is to visit the left descendants of N2. That's all done. So now we're going to visit N2 itself. And so that'll be our fourth node that we output. Guess as to where we're going next. N5, yep. All right. So now we've kind of done this whole left side of the tree. We'll go back up to N1, which we will visit. Since we have visited its left, now we visit it. And next we visit the right, which it does have the right. And so as we go here, we visit N3. And remember, each time we come into a node, we're starting at the beginning of these instructions, right? So the first thing we need to do at N3 is say, visit your left descendants. And it does happen. So we go to N7 instead. N7, same thing, we're starting over. We need to visit the left descendants. It's not really to the left, but just pretend it is. So it does have it in B. So we get to NB, we say visit your left descendants, no descendants, right? So then we can visit the node itself. And so we output NB. Where do we go next?
Back
That's it.
So we visit N7 after that,
N3.
N3, and finally
8.
N8. And so that is your in-order traversal of the tree, of a binary tree. All right, last one. Post-order. So in this one, we visit the descendants, and then we visit the node itself. So we will start with N1, which means that we, again, are going to come all the way down to N9 as we propagate through. So we say, N1, we need to visit the descendants. We're going to go left first here. N2, we need to visit its descendants, going left first. N4, same thing here. Finally, we get to something that doesn't have descendants, so we can print it out. And so as we come along here, we need to visit all the descendants, right? And so NA is a descendant of N4. Now we come back up. What comes next?
N4.
Yep. It's N4, because we have done the first instruction for N4, right? We visited these two, so now we got to output N4. After that,
N5 and N6.
N5, yep. So we went back up to N2. We're still visiting its descendants. N6. Now that we've done all of this, who's next?
N2.
N2, yep. And now?
N3.
So we've visited all of these descendants of N1 on the left. Then we've got to go on the right. But remember, once we get here, we're still headed down this left side. So we go all the way down to NB. Okay, after that,
N7.
N7, yep. And then N8. And then N3, and finally N1. And so that is the post order. And these are all just a little bit, they're slightly different. So let me show you the easy way to do this. All right. So if you need to do this traversal on a tree, and I'll go ahead and file a complaint. So Keynote, the presentation software I use, I really like, but it doesn't seem to have a way to do annotations when you're on the computer. So if I'm using a tablet with it, it's great. I can draw and stuff, but it seems that, at least in this version, Apple has decided maybe not. So here we are in just the image editor. So what you want to do, if you're going to do a traversal of a tree, first thing you can do is for each node, I'm just going to draw like this. Now, you won't have to do this once you know the trick here, but this is helpful just to remember it. Maybe I should have used a smaller tree, but... Okay. All right, so I'm drawing these weird 3 lines on everything. Did it make that one an arrow?
Yeah, it did.
How did it do that? What is that? I don't want that. Okay. Interesting. Okay. So now that we have our 3 lines here, the way that you can approach this is we're going to start up here at the top, and we're going to draw around like this. So we're just going around the border of this visual of the tree. I'm going through these lines as they happen.
This one is pre-ordered.
The tree itself?
Oh no, you're doing traversal. You're doing left node right.
So I'm not doing any specific one yet. So this will actually cover all of them.
I thought that's what you were doing with the lines.
Yes, I am. That is what the lines are for. Yeah, sorry. Look, it changed it to yellow. Oh, okay. Is there like an easy way to change that back? Or... Okay. Good. Okay. So let me get my line needs to go through there. So it needs to. Oh gosh. All right. So this line is going to come through here first and then go back. Just going to imagine that. So what you want to do, now that you've drawn this lovely thing, if you were doing the pre-order traversal, you're looking at these left lines here, right? So you just go from the start to the end, and as you intersect those lines to the left, that is the order in which you display things. So if we're doing pre-order, it's going to be N1, N2, N4, N9, then NA, N5, N3, N7, NB, N8, just like that. Now, if you're doing in order, it's the line pointing down. So you can see immediately, you follow your line all the way down. Here's the first one to come through. So N9, N4, NA, and so on. If you're doing post order, it is the line to the right. Just remember that you still start going left, right? So you come all the way down here, crossing that one first. So you don't really need to think about it much if you've got a picture. You can just draw this out, follow that line as it intersects, and you can get the pre-order, the in-order, and the post-order of traversal that way. It's a lot easier than thinking through it for each level. Obviously, we'll write the code to go through it, and kind of the point of code, right? We understand it when we write it, and we know it's correct, and then we use it, and we don't have to think so much about it until we need to do something in depth with it again.
Which leg again? The left, middle, and right is pre-order, post-order?
Yeah, so left is pre, down is in, and right is post. You guys seen this trick before? Oh, wow. Hey.
Doing it mentally.
Yeah. I don't know. It's a good CS trick, I guess. I don't really know a lot of CS tricks, but this is one of them.
That's a scary hand.
Yes. I didn't really think about what it would be.
Some
Yeah.
hand players.
Yeah.
Will that be like, will you have that trick written?
Yeah. We'll have this at the very beginning of next class, and I'll just show it done with like it written out how it's done, so you have it as a reference. It'll also be like on your study guide for the exam or whatever. But yeah, handy trick there. I believe that is all I want to cover today. Yes. Okay, so next time we will do binary search trees. Please do your programming challenges if you have not done them. And if you need anything, help with them, you've got TAs, SI, and you've got me, so let one of us know. We're happy to help. But I will see you guys on Monday.